Hello everyone, welcome to Lesson 9-2, Theoretical and Experimental Probability. This lesson we will continue to answer how can you predict the outcome of future events, and we will work with the vocabulary uniform probability model, theoretical probability, and experimental probability. The place where you might deal with probability would be at a fair or a carnival. So let's take a look at carnival games for a real world example. The prize wheels for a carnival game are shown. You receive a less expensive prize if you spin and win on wheel A. You receive a more expensive prize if you spin and win on wheel B. Now take a look here. Wheel A, you receive the smaller prize if you win, but look at the probability. Okay, it's divided equally into 4 sections. 1 you win, you lose, you win, you lose. So the chances of winning and losing are the same. They're split evenly. While on wheel B, you notice that the parts that say that you win are much smaller and you lose are much larger. Okay, so here it almost seems like you have only 1/4 chance of winning. This is about 1/8, and this is about 1/8. So you really only have about 1/4 of a chance of winning, while here you have about 50-50 chance, right? Let's take a look at our first vocabulary word, uniform probability model. In a uniform probability model, each outcome has an equal probability of happening. So uniform is implying that it's equal, the same, it's united. Which wheel has uniform probability? Wheel A or wheel B? Well, this one has uniform probability because you have a chance, equal chance to lose or win. Question 2. Use a paper clip and the tip of your pencil to spin each wheel 4 times. Record your results. So, if I were to spin here, okay, I could record my probability here and spin here, probability here. Now, for the sake of time, we're not going to do this. But you can predict which wheel you'd have the greater probability in. This is something we could do in class as a group. And you can see over here the greater probability of landing on win and lose is 50-50 chance. While here, it's not. You're more likely to land on you lose. So with that being said, why do you think winners on wheel A, right here, receive a less expensive prize than winners on wheel B? Well, the likelihood of winning a prize on wheel A is greater, simply because over here is 50-50, while over here is only about 25%. So because there's a greater chance of winning when you spin this wheel, more people are going to win, so you have to give cheaper prizes. If you give the expensive prizes out for wheel A, you will not make very much money as the host of the game. Let's take a look at the main idea of this lesson by also exploring some of the vocabulary. Theoretical probability is based on uniform probability. What should happen when conducting a probability experiment? Experimental probability is based on relative frequency, so we relate it to other situations. What actually occurs during such an experiment. So we have theoretical, it's based on theory, okay? We use theory, and we use uniform probability, like on wheel A. There's a 50-50 chance. So we can theorize that if we spin the wheel 2 times, there's a chance that you will get, you will win, or you will lose, or you will lose, or you will win. We can kind of predict all the probabilities, all the outcomes for theoretical probability. For experimental probability, it's the actual number that occur. If you spin 4 times, you could actually lose all 4 times. So it's the actual outcome. So experimental versus theoretical. The theoretical probability and the experimental probability of an event may or may not be the same. As the number of attempts increases, the theoretical probability and the experimental probability should become closer in value. Let's take a look at example 1. The graph shows the results of an experiment in which a spinner with 3 equal sections is spun 60 times. Find the experimental probability of spinning red for this experiment. So here's our spinner, right? We have the little spinner in the middle. We flick it with our finger, it spins around, and it's likely to land on green, equally likely to land on red, or equally likely to land on blue, because it's split into 3 equal thirds, right? Into 3 parts. So the graph indicates that the spinner landed on red 24 times, blue 15 times, and green 21 times. And they made a bar graph, right? Spinner results, green 21, blue 15, and red 24. So here we're going to use what we learned in lesson 1, okay, our probability ratio. So if we have red, probability of red, number of times red occurs to total number of spins. So we know that it's 60, and then we have red 24. So we write 24 over 60. And when we simplify that, okay, we find a common multiple between these two, and we see that it's 12. 12 goes into 24 2 times, and 12 goes into 65 times. So it's 2/5. So out of 5 times that you spin it, 2 will be red. Okay, the experimental probability of spinning red is 2/5. That's the experimental. After doing the experiment, we found that it was 2/5. But in theory, it should be 1/3. Am I not correct? So theoretical probability, we say that 1/3. So for every 3 spins, it would be 1. For every 6 spins, it would be 2. You understand? But the experimental, the actual result is 2/5. Part 2. Compare the experimental probability you found in example 1 to its theoretical probability. We just talked about that. The spinner has 3 equal sections, red, blue, and green. So the theoretical probability of spinning red is 1/3, 1 out of 3 chances, right? Since 2/5 is about 1/3, the experimental probability is close to the theoretical probability. See, 1/3 would be 2/6, right? We would write 2/6. That's the same thing as 1/3. It's very close to 2/5. Not exact, obviously, but it's quite close. Okay, let's try the practice on our own. Refer to example 1, right here. If the spinner was spun 3 more times, so 63 times now, and landed on green each time, find the experimental probability of spinning green for this experiment. So what is the experimental probability if we change green to 3 more times? So green would go up to 24. Okay, green would go up to 24, and now it's over 63. Okay, our probability is over 63. And they want us to find the experimental probability of spinning green for this experiment. So now green is 24 over 63, right? Probability of green. So it would be 24 over 63, and if we were to simplify that, I know that both these numbers are divisible by 3. Divisibility rule states that if you add both numbers and you get a factor of 3, they're both divisible by 3. So 2 plus 4 is 6. 6 is a factor of 3. So that's divisible by 3. And we know that 24 divided by 3 is 8, right? And if we add the 6 and the 3 together, 6 plus 3 is 9. 9 is a factor of 3. So this is also divisible by 3. And 63 divided by 3 is 21. So 8 to 21. Meaning if I spin, for every 21 times that I spin, I'm going to get 8 green. Is this about 1/3? Would you say this is about 1/3? Remember, there's 3 options. 1/3 would be 8 over 24, wouldn't it? So compare the experimental probability you found in exercise A to the theoretical. Well, theoretical would be about 1/3. Am I right when I do this, in doing so? It is. This is about 1/3. It's not a half, right? And it's not a quarter. A quarter would be 8 over 32. This is closest to 1/3. Well, a half would be 8 over 16. So no, it's not closest to a half. The closest one is 1/3. Example 3. Two number cubes are rolled together 20 times. These two number cubes are rolled together 20 times. A sum of 9 is rolled 8 times. So a combination of 9 between these two. So yeah, 4. We have to consider all the combinations of these two that can make it into 9, right? What is the experimental probability of rolling a sum of 9? Well, the experimental probability, when it's rolled 20 times, right? It was rolled 8 times. So it's going to be 8. The number of times 9 occurred on the top and the total number. The total number goes to the bottom, which is 20 times, as you can see here, 20 times. And it was rolled 8 times. So when you simplify this, you have 2 4s here and you have 5 4s at the bottom. So 2/5. The experimental probability of rolling a sum of 9 is 2/5. So for every 5 times I rolled it, I should have gotten 9 2 times. Example 4. Compare the experimental probability you found in exercise 3, or in example 3, to its theoretical probability. If the probabilities are not close, explain a possible reason for the discrepancy. When rolling two number cubes, there are 36 possible outcomes. The theoretical probability of rolling a sum of 9 is 4 out of 36, or 1/9, right? Rolls with sum of 9. Here's all the rolls for the sum of 9. The first cube could be 3, the second could be 6. First cube could be 4, 5, 5 and 4, 6 and 3. So really there's only 4 different combinations to get 36. To get 9. So there's 36 combinations in total. Since 1/9 is not close to 2/5, the experimental probability is not close to the theoretical probability. One possible explanation is that there were not enough trials. You didn't do it enough times. Okay, in example 3, what is the experimental probability, after doing the experiment, of rolling a sum that is not 9? Well, rolling a 9 in the experimental is 1/9. Oh no, this is the theoretical. Okay, this is the theoretical. In the experimental, it was 2/5. 2/5 of the time. So in the experimental, it would be not 9, would be 3/5. It would be the difference of this. So 3 out of 5 times, when we did the experiment, we would not roll a sum of 9. Okay? So that's your answer there. For D, 2 coins are tossed 10 times. Okay? You have these 2 coins tossed. Both coins land on heads 6 times. Compare the experimental probability to the theoretical probability. If the possibilities are not close, explain possible reasons for discrepancy. Okay, so 2 coins are tossed 10 times. Right? Both coins land on heads 6 times. So when we look at the possibilities of the coins, or the combination that we could get from tossing a coin, when you toss 2 coins up, okay, you can get them both heads, so head and head. You can also get both tails, tail and tails. You could have this one land on head and this one land on tail, so head, tail. Or you can have this one land on heads and this one land on tails, so you would get tail, head. Okay, so there's 4 different combinations. Now, if you throw it up 10 times, you multiply these 4 different combinations times 10 times. So there's 40 possible combinations, right? Total number is 40. Now, both coins land on heads 6 times out of 10, so that's 60% of the time, right? Compare the experimental probability to the theoretical probability. In theoretical probability, okay, it's 1 out of 4 chances that they would land both heads. But here we get 6 out of 10, which is 3 out of 5. So right now, for the experimental, when the coins were tossed, it was 6 out of 10, which is 3 out of 5, right? It's 3 out of 5. But in reality, it should be only 1 out of 4. That's theoretical, because there's only 4 different outcomes. So 1 out of 4, right? 1 out of 4. 1/4 compared to 60%. Do you see the difference? Okay. If the probabilities are not close, explain a possible reason for the discrepancy. Well, what's the difference for the discrepancy? I would say we probably need more trials, because the more that we do something, the greater chance it will match, the experimental will match the theoretical. So that would be my discrepancy, the reason why I think. But in reality, because it's theoretical is 1/4, I don't really think, I mean, in theory it should get closer, but I see it being very difficult for 1/4 to come up all the way to 3/5, to 60%. Question C. Suppose 3 coins are tossed 10 times. Now it's 3 of them, right? So we have to write out all the different possibilities that we can get for 3 coins, okay? All the possibilities would be all these possibilities. All 3 coins could land on head. All 3 coins could land on tail. The first one could be head, and then the next 2 tails. The first 2 could be head, the last one tail. The first one could be tail, the next 2 head, 2 tails, 1 head, head, or tail, head, tail. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities. So just by including 1 coin, we've added double the number of possibilities. So suppose 3 coins are tossed 10 times. All 3 coins land on head once. So we get this one, okay? 1 time out of 10 tosses. If the probabilities are not close, explain the probabilities why. So compare the experimental probability to a theoretical. Theoretical is 1 out of 8, right? That's the theoretical, 1 out of 8. And over here it says that we got 1 time the experimental 1 out of 10, right? So 1 out of 10. Is this close? Well, 1/8 is about 12%, 12.5%, and 1/10 is 10%. 10% and 12.5% are pretty close. We're only off by about 2.5%. So they are close. If the probability are not close, explain the possibility why. So even if we had tossed it 8 times, there's a good chance that of those 8 times that we could have gotten at least once, right? So what are theoretical and experimental probabilities good for? Theoretical and experimental probabilities can be used to make predictions about future events. Okay, we use theoretical and experimental to predict the weather, to predict the plant growth of plants, to predict how certain medications can work. Okay, and that's why we have trials, clinical trials, and so on. They help us predict the future. Example 5. Last year, a DVD store sold 670 action DVDs, like action movies, 580 comedies, 450 drama, like sad movies and whatnot, and 300 horror DVDs. A media buyer expects to sell 5,000 DVDs this year. Based on these results, how many comedy DVDs should she buy? Explain. Okay, what we need to do is we find the sum of all the DVDs that were sold, right? And we create a ratio between, so they're asking us, we create a ratio of the comedy DVDs compared to the sum of all the DVDs. So what I see right now is that I have 580, okay, comedies DVDs compared to 1,800 total DVDs. So all I did was just take the sum of all the DVDs. 670 plus 580 plus 450 plus 300. Okay, so 500. About, I would say about 1/3. Close to 1/3. So what would be 1/3 of 50? About 16, right? About 1,600. So based on the results, how many comedy DVDs should you expect? I'd say about 1,600. So here's what they did. They took 5. Oh, they're saying over 2,000. Did I do my math wrong? I might have. I have here 670 plus 580. That's 1,250. 1,250 plus 300 is, oh, I did. Yes, I did my math wrong. This would be 1,550 plus 450 is 2,000. Yes, this is wrong. So we go replace that with 2,000. Now that's just slightly over a quarter, right? 500 of 2,000 is a quarter. This is just slightly over a quarter. So when we simplify 580 over 2,000, we get 29 over 100, right? That's dividing both by 20. And then we do a ratio. What do I do to 100 to make it 5,000, right? And I have to do the same to a 29. And when we do so, we see that we should order about 1/4 or slightly over 1/4 of 2,000 of 5,000, which is 1,450. She should buy about that. So this is how we it helps us predict how many DVDs this store owner should buy. And here you have the guided practice that we will look at in class. If you'd like, you can read ahead and see if you understand the questions. If not, please ask in class. See you then.